Okay, let's take a look at the following problem. Here is a circular flat disk with charge density on the surface. And the question is, what will the electric field be in the point P here? And how are we going to solve this problem? And what will you learn? What the tricks we need to use is first, see the symmetry of the problem. And second, we need to learn how to use infinitesimal elements to sum all those elements by integration. So it's not going to be so simple, this problem. But if you will understand everything here, you can basically solve any similar problem later on. So let's look at the circular part somewhere in this disk, like this one. This is the infinitesimal element that I'm gonna use. Note that the radius here is A, but it's capital R for the whole disk here. So I'm choosing another radius A, which we can vary. It can be any value here, 0 or half or whatever. So it's also having a certain distance here, dA, the width, or here if you like, the width is dA. And the distance around here is the standard 2 pi times the radius. So that's the infinitesimal element. And when we put this here, so here I'm just showing a part of that circle. It's really actually something like that. But let's follow here, A here, that's A here, and then upwards C, that's the height here to the point, so that's that C. And the distance from, say, a charge here, in that point to the capital P point here, is, according to Pythagoras, that's this one. That one is squared, and that one squared, square root of that. And if you have a charge here, then the electric field in that point will be in this direction. It's sort of how I put the electric field here. And from a charge here, you will have the electric field direction over there. And what you can see, there is a pairwise cancellation here. Here you have a component here in the electric field, but here you have the component in the other direction. If you sum this pair, so those orthogonal fields, they will cancel. And then this one has a y direction and also that one, and they will be added. And if you think about every pair, when you rotate that kind of thing around the z-axis, it will always be the electric field, the orthogonal electric field will cancel, and there will be only contributions in the z direction. Here is z, here is the xy plane. So that's the thing here. So then we understand what I wrote here. The total electric field from such a ring here, that will be in the z direction. And also what we can see here is the sine function of theta. Here's theta, and that is c divided by r. But if you look here, the electric field from a point charge here, it will be in that direction, and it will have a component like that, and then this. And you can see it is exactly the same angle theta here for the electric field as it is here for that triangle of distances. So the sine theta, if you think about theta here, that will be this dEz divided by that, just like I said here. So it means that this one here will be like that. So that's for single charge on the ring. And note that if we took a look at the other charges around the ring, it will be the same angle theta all the time, right? So this sine theta, it will always be c over r for all the charges, not only this one that I showed you. And so for single charge, Coulomb's law says that, yeah, if that charge is qc, so let's say, yeah, divided by 4 pi e naught and the distance r, so that's the electric field here from the charge. But since we know pairwise the orthogonal direction here for one charge here and one charge here, the field in this orthogonal direction, let's call it x direction if you like, they will cancel. So there will only be, the only thing we need to look at is in the z direction. So that will be done by multiplying with c over r here. So here you have the contribution in the z direction from one charge, but we are really interested in the whole ring, aren't we? So we will have to sum all those electric fields in the z direction. But all charges will have the distance r. When you sum, it will not change, and all will have theta, so it will not change. So z over r is the same, and when you sum all of them, yes, you can see the height c here is of course the same all the time. So the sum of the fields, it will just be the sum of the charges here, because that's a constant. So the sum of all the charges around the ring is of course the charge of the ring, isn't it? So the total charge of that ring, and here this ring is an infinitesimal element, so it's not a very big charge, it's a very thin ring here. So that's why we call it dq here. It's an infinitesimal charge, it's a small charge. And in the problem we were given that there is a charge density sigma, and the charge density times the infinitesimal area element, yeah, that is the charge, sigma dA. Okay, and this area element, or surface element, for a ring is just the distance around 2pi times the width dA. So you see that here, 2p dA. And sigma is constant over the whole disk, So it must be the total charge of the disk divided by the total area, which is pi r squared. So now we know a little bit more about the ring. Here is called the Q, and here the sum of the point charges, that's the charge of this ring, but we call it dq now. So it will be this formula, as you see here, but we call it dq because it's a small charge, and also the contribution, the electric field is small, so we call that DEC. So let's see here, okay, r squared and r here, that's r cubed. And the C, I'll put that there, and then the Q, we use that on the top of the page. Remember, sigma 2p a dA. That's the Q. Okay, and yeah, that can be simplified, 2 pi there, 4 pi there, so that's a 2 e naught c sigma ADA is still there. So it's that. So in order now, so this is the contribution from one ring. Yeah, okay. This one here, it's somewhere here. What is one ring giving? What kind of field here? That's what we have done now. So this is that contribution to the electric field from one ring of radius A and width dA. But now to get the whole circular plate, we need to sum all the rings, and that we can do by integrating. So in order to do that, we integrate here and here. So here you sum all those, so you get the total electric field in the z direction. And integral here, but some of those are constants. C, the height is a constant, the charge density is constant, 2e naught is a constant. Okay. A is varying, that's the radius of the ring. And also the distance to P is depending on A, so that's varying. If you have a large A, then the distance is something, another A, something else. So this is a variable. C is constant, yes, but A has a variation here. So that must be included in the integral. So that's the r cubed here. Yeah, that's square root of that, but cube, then you get 3/2 here. Okay. And then it turns out that this ohm complex function has a very simple primitive function. It's just that one here. And you can test it yourself to see if you take the derivative here, you must get this. And you can test it. It's incredibly simple. And we want to sum now all those contributions for various A's, where A is small, 0, all the way up to capital R, the total radius of the plate. And here's the primitive function. And now we can put in that. So you put in R here, then minus with 0. A is 0. So yeah, that will be 1 over C. So here is my result. And again, I remind you that sigma is this number here. And then in the problem text, let's check if C is very large. Yeah, if this point is almost at an infinite distance, the plate here will look like a point charge, right? So then Coulomb's law should say immediately that yeah, the total charge of the plate looks like a point charge, and divided by 4 pi e naught, and the distance then is c squared. So, okay, so that formula here should basically approach this here. Is it true? So let's take a little look here. Yeah, here, let's study the square root of that function here. So that can be written like this, if you like. Then you can get out c here. So you have the square root of this. And maybe you remember that the square root of 1 plus x is simply 1 plus x half, etc. But we just take the leading term here. So you have c, and then you have this down. Okay. So then we should put it here. Okay, here's the full formula again. Let's put in that result here. Okay, that's done. What happens then? Yeah, that c and that c cancels, right? And then 1 over 1 plus something, let's call it 1 over 1 plus x, can also be a Taylor expanded, and that would be 1 minus x. So c disappears, and that guy which is left will be 1 minus x, or 1 minus whatever is what we have here, that one here. So that's that. That is still here. And when we multiply that in here, then you see immediately that term will cancel with that term. So then it will be this times that, but that will be positive, minus and minus here, positive, and you get this. And then finally we can use that the charge density is the total charge divided by the total area of the disk. And what do you get? You get exactly this one. So the formula works great, in other words. It really was. Coulomb's law came back. And also, we should check here what happens if the disk becomes infinitely large. What then? And here is the full formula. But if you let r go to infinite here, yeah, then the whole term here will go to 0. So you will just be left with this. Sigma over 2 E naught. No, that's exactly what we got here. Okay, like, subscribe if this helped you out a little bit.